Okay, is the screen share working?
Yep.
Yes.
And recording is on? Okay. 1 second. Okay. Yeah, today we'll be going over 3.3. This is talking about the complete solution to any system of linear equations. So if you have xp, the vector xp, such that it is a solution of any system ax equals b, then every solution of ax equals b is in the form x equals xp plus xn, where xn is any member of the null space of the matrix. There's a proof for it. And the converse of that also applies. If you have xn belonging to the null space, then xn plus any solution to the system ax plus b equals b. Okay. Xn plus any solution to the system ax equals b will also be a solution to the system ax equals b. A matrix A is said to have full column rank if each column is a pivot column, and that means it has the system has no free variables, which also means it has no special solutions to ax equals 0. It means the null space is a set containing only the 0 vector. It means the rank of the matrix is the number of columns in A. It means the number of columns is greater than or equal to the number of rows. And it means that all columns are linearly independent. And finally, that you'll have the REF of this matrix will be either the identity matrix or the identity matrix plus a few zero rows at the end, at the bottom. And it means that the system ax equals b will have either one solution or 0 or 1 solutions, depending on if you have 0 rows at the REF or not. Similarly, a matrix is said to have full row rank if each row in the reduced row echelon form has a pivot. And when this happens, all rows are linearly independent. The rank is equal to the number of rows in the matrix. There are n minus m special solutions to ax equals 0, where n is the number of columns and m is the number of rows. And the number of rows is greater than or equal to the number of columns. And the reduced row echelon form of A is either the identity matrix or the identity matrix with some free columns wherever, just placed wherever except for the first column. And also the system ax equals b always has a solution, either one solution or infinitely many. Yes. One unique solution or infinitely many. Here, if the system has full row rank, then the number of solutions is exactly 1 if and only if the REF is exactly equal to the identity matrix. But for column rank, you can have, yeah, go ahead. You kind of do for REF. Yeah, right. I think so. Oh yeah, that's REF, not RREF, but just row echelon form. Sometimes, well, depends on what you're trying to find. If you're just trying to find which columns are independent, I think REF is sufficient. But if you're trying to find like I can't remember exactly what REF. Okay, I think I'll go back to 3.2. Uh, REF is when you can have, for example, a 2 as a pivot, or you can have a non-zero value above a pivot. But in REF, uh, all entries in the pivot columns must be either 1 if it's the pivot column, or 0 if it's not the pivot. And kinda, yeah, right. But those have to be at the bottom. Okay, yeah. Basically, the RREF is as close as you can possibly get to the identity matrix. Is that all for? Okay. Uh, matrix A. What? Matrix A has full column rank if and only if the columns are linearly independent. Good to know. And matrix A has full row rank if and only if the rows are linearly independent. That's good to know as well. What was your question? Yeah. Well, that's one way you could do it. There's well, if you're gonna go just based on the definition, then before let's say if we hadn't learned this theorem and this theorem, right? All we would have had to find all the only tools we would have had to find to determine whether or not a matrix has full row rank or full column rank would have been the definition of full column rank. And the definition states that a matrix has full column rank if each column has a pivot column. The, and the way you'd find this would be uh, I think it'd be exactly the same as finding out whether or not the columns are linearly independent. Yes. Well, I don't think you can go back. I don't think you can go backwards with these. Um, you can't really say that just because the number of you can't say just because the number of columns is greater than the number of rows. Or no, I'm not sure. Because it says any full any matrix with full column rank has a property such that m is greater than or equal to n, right? You can't really say that because a matrix B has m greater than or equal to greater than or equal to n, that implies full column rank, because that's not true. It may not necessarily be true. Yeah. Okay. Even then, I'm not sure. Probably. Okay. Yeah, yeah. To disprove it. Yeah. 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 To disprove it, you will need to fail one condition. That's that's all. We should do problems. My professor gave us a bunch of problems. Just one problem. Yeah, and then we have the recommended problems. Okay. Um. Yeah. Let's take like. Yeah. I don't remember. Yeah. I think we used some of my professor's problems last time. Yeah. Yeah. Let's take like 5 minutes to do this. Wait. What's the question? Okay. We have to find A and B. Okay. Yeah. Let's take like 5 minutes to do it. Okay, is everyone ready? Yeah, I couldn't either. So I looked at solutions. Um, yeah, yeah, we are going backwards. Yeah. So I guess what's happening here is we recognize that the null space is equal to the span of this vector, and then we set some constant as a coefficient of this vector. Uh, we okay. No, we converted from a span to a set of all vectors, all linear combinations of this vector, and then we substitute the variable inside the vector using the product of the scalar multiplication, and then we kind of generalize, I guess, and 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 we write the other variables in terms of this free variable by saying x1 equals 2x3, x2 equals negative 4x3, and so on. From here to here. Oh, we just say let x1 equals 2x2, x3. Yeah, we're given 2x3 and negative 4x3, right? You just say let x1 equals 2x3, let x2 equal negative 4x3. So, and it's the set of all vectors in this form. Uh, and then we convert it from this set to a set of all vectors x, where this matrix times the vector equals the 0 vector. Okay, this makes sense. We we write these equations as a system of equations. X1, it goes from x1 equals 2x3 to x1 minus 2x3 equals 0. So x1, yeah, right. I think she skipped a step. Uh, I mean, she can, but it's kind of hard for us to understand. But basically, if you were if you were to fill in the missing step, you'd write these two equations as x1 minus 2x3 equals 0, x2 plus 4x3 equals 0. then you recognize that you could write that system of equations as a matrix equation. So where x, the vector x is x1, x2, x3, and this matrix times that vector would equal the 0 vector. And then you can add a 0 and it doesn't change the null space. Well, no, it's not that it doesn't change the null space. It's because, yeah, it doesn't change the null space because the null space is a set of all solutions to ax equals 0.
Maybe because
Anything.
they, sorry, I'm interrupting
Yeah, go
you.
ahead.
So maybe because in the question they have mentioned that it's a 3 by 3 system, so
Yeah,
we have
yeah,
to add a row of zeros in there.
that's why. Yeah. Yeah, I mean, this matrix does satisfy ax equals b. Well, it does not yet because we haven't defined b yet. But this matrix satisfies the property that the particular solution is. Yeah. Actually, no. The only thing we found with this matrix is that the special solution is this. The next thing we do is get it to 3 by 3. That's by adding a 0. And finally, we satisfy that the system has a particular solution 1, negative 1, 1 by defining a b such that this particular solution times this matrix equals b. We just find b. In the problem. It's yeah, it's given to us. Yeah, we're given I mean, we've found the matrix. We're given x. We need to find b, so we just multiply. Yeah, it takes time. No, but I think it would have been really helpful if we hadn't skipped this step. Yeah, the thing is, like, I'm good at like walking through this problem and understanding what happened. But if you were to ask me to replicate this on my own, that would take a while. Yeah. Any questions?
So you got back to B by doing the dot product of the last two matrices, or how do you get B again? Sorry if I missed it.
Just multiply. Matrix multiplication.
Okay, cool.
Yeah. Yeah, because we're given, we know ax equals b. We're given x. We found a. We need to find b. Just multiply.
That makes more sense now.
Yeah. Yeah, it's always, for me, always going from null space to something or going from something to null space is always hard. Yeah, any questions before we move on? Cool. Okay. Yeah, so let's work on the recommended problems from the textbook. I think this will take a while. Yeah, I'm opening the book. Yeah, let's do number 1. Let's find the complete solution. Wait. Okay, this works. Yeah, yeah, yeah. I mean, and in 3.3 they haven't introduced the term basis because that comes in 3.4. So they have to tell us how to describe the null space without using the word basis. And I guess, well, I'm pretty sure basis is the way to do it. Yeah. So let's do number 1. We need to find column space, null space, and complete solution. Take 5 minutes. This is 3.3 problem 1. Is everyone ready? Okay. I'm able to get it, but it's just gonna take a while. I'll just show what I have so far.
Did you do RREF or just do REF? I think for this one we didn't have to go all the way to RREF, right?
I think you do because you want to find the particular solution. I went all the way.
Okay, cool.
This is equal to. Right. Yeah, so to find the particular solution, you do use the b value they give you, which is what I did, 4, 3, 5. To find the null space, all you really need is the I think the REF. You don't, I mean, you really don't need to set up this thing with zeros because whatever you do, any row operations you perform on the matrix, you'll still get the zero vector at the right side, right? So it's not really necessary because it won't change. What you're really only looking for, yeah, this isn't mathematically correct. This is equal to REF of A augmented with the particular solution. Yeah. So on the left you have the reduced row echelon form of the matrix A, and then on the right side you have the particular solution of the system of equations. If my math is correct, yes. Oh, there is another 0 at the end? Okay, that makes sense because um, the fourth column is free. Wait, this doesn't make sense. Right. The third and fourth are free, right? Wait, I'm just trying to see. 8
No.
minus 4 is 4, right? 8 minus 5 is 3. 8 minus 3 is 5. Yeah. Yeah, so the third and fourth columns can be all zeros. That's fine.
So I don't understand why do you have to go through the last two steps since you already got 4, -1, and a full row of zeros there on step number 4.
That's because you want to find the column space. Because you want to find the special solutions of the matrix. That's why I went all the way. Because the next step would be to describe the complete solution of the system using the column space. And to find the column space, you need to set x1. Well, you need to say x1 plus 0 plus x2 minus 2x3. Or no, x1 plus 0 plus x2 minus 2x. This should be x3 minus 2x4 equals 0. And you really need those relationships.
Okay. Okay. Gotcha.
Is this? Is this it? Um. Oh, okay. S1 and S2 are special solutions. Null space. So I didn't go that far because I didn't want to take that long. But yeah, yeah. Okay. All I did was find the reduced row echelon form of A, and found the particular solution. That's not enough to find the answer to this problem. What you need to do is then find the column space and the null space. The column space of A. Well, actually, you don't need to find the column space. Or actually, no, you do. They ask you for it. They explicitly ask you for the column space, so you do need to find it. Yeah, but if you're just if all you're doing is finding the complete solution, you don't need the column space. But since they are asking you for the column space, I mean, column space is just this is the span of this vector and the span of this vector. Now, to find the set of all solutions, the complete solution, you need to find the two special solutions to the system AX equals 0. And to do that, you need to find the column space. To find the column space, you need to set this equal to 0. This times something equal to 0. And that would give you is it will give you a system. Yeah, a vector. Yeah. Let's see. Actually,
So I guess we had to keep that B1, B2, and B3 in terms of B1, B2, and B3, and not the values for them.
um,
Mhm.
let's see.
Yeah.
Yeah, the extra 0 is not necessary because you need because you have 4 columns, and the solution to AX equals B must be must have the same size as the row of the matrix. So we found the particular solution, which is 4, negative 1, 0, 0. I'll write that down. We found the particular solution. Now we want to find the special solutions to this system, basically. And the way we do that is just well, we multiply this matrix, not the whole augmented matrix. We multiply this matrix, which is the REF of A, by a vector called XS, which stands for special solution. And we set that equal to the 0 vector. But and then what that gives you is this matrix equation. And basically, we want to find the null space of this. The way we do that is, well, we first recognize that these two are free. These two columns are free. These two are pivot columns. Right. So we set these equal to 1 and 0 respectively. Right? Is that it? wait, no, that's not what you do. You say x1, no, you want to write this equation from the system of equations, from this matrix equation. This should be a system of equations right here. But then you solve this in terms of the free variables. So you say x1 equals negative x3 plus 2x4. x1 equals negative x3 plus 2x4. And x2 equals negative x3 minus 2x4. Right? And then we also recognize that x3 and x4 are free. And then we write the column space as the span of a generic vector consisting of x1, x2, x3, x4. Actually, no, not as one generic vector, but we write one generic vector. It doesn't necessarily span the column space, but we have negative x3 plus 2x4 and negative x3 minus 2x4 and then x3, x4. Right. This will be a vector in the null space, a vector in the null space. Um. No, I think I'm doing exactly what they're doing. I think this looks pretty similar to what I have. But then you write this as two different vectors, right? So one containing x3, one containing x4. So negative x3, negative x3, x3, 0. And the other vector is 2x4, negative 2x4, 0, x4. Right? And then these are your particular solutions. Your particular solutions are negative 1, 1, 0, and 2, negative 1, 0, 1. And from here to here? Yeah. So you write, well, okay, x3 and x4 are free, right? So they can be whatever you want them to be. You set x3 equal, you write two different vectors because you have two free variables. In one vector, x3 is 1, x4 is 0. In the other vector, x1 is 0. Or sorry, x3 is 0, x4 is 1. Well, yeah. Well, I think so. I definitely learned it in problem section. Yeah, and from here you factor out the x3 and x4, so x3 3. Right, and these should be what they got, right? -1, -1, 1, 0, 2, -2, 0, 1. Yep. These are your special solutions. Yeah, and then to find the complete solution to the system of equations, it's just your particular solution, so this, plus all linear combinations of these two vectors. So yeah, and the way they want you to write your answer, I'm pretty sure, is like this. You want to write it as a set. So it's a set, and you want to write in the form. So first you have your particular solution. So 4, -1, 0, 0, plus your special solutions, -1, -1. Plus 2, -2, 0, 1. And now you don't want to forget the coefficients in front of the special solutions, x4 and x3. This is the complete solution to ax equals b. Yeah, that's a long problem. Any questions? Yeah, so in short, what we want to do is find the reduced row echelon form of the matrix, and at the same time find the particular solution by augmenting the matrix with B, and then that will give you the reduced row echelon form. Use that to, right. Now that I think about it, what would you do if, let's see, what would you do if the second column were free and the other two were not? I don't think that process works. I don't think you can augment this matrix. How did they do it? Oh, this is okay. They did the same way as I did.
So if you look at problem number 3.3a worked example, they have augmented it. It's a similar question.
What's the example?
3.3a worked
Okay.
example.
Yeah.
It's on page 154 at the bottom.
Yeah, I see it.
Yeah.
Okay, so this is the way they did it. Oh, and okay, since this zero has a, since this last row is all zeros, it always has a solution. Okay. Yeah, that's interesting. I still, yeah, I still need to think about why that works, but as long as it works, I'm fine. No, they probably will. I think so. Yeah, there will definitely be a find a complete solution question. One can hope. Yeah, exactly. Expect the worst and hope for the best. Yeah. Number 4 is basically the exact same. Number 10. Yeah. Yeah, I'm thinking 10. What else? There's wait. Yeah. Yeah, we did. I'm looking to see what else is on the recommended problems. How many we might need to do to allocate time. Yeah, I think we can finish with 10. Yeah, let's take like I mean we have time. Let's take like 15 minutes to do 10. Okay, how's everyone doing? I think I got a solution, but I think it doesn't work now that I check my work. Yeah, but they didn't write their method of finding their solution. They just wrote a solution, but they also said many values of a possible. I don't know. I haven't looked. Oh yeah, yeah. Well, same with 3B. Yeah, yeah. Okay, yeah. 30 if 301 is a special solution, then any multiple of 301 is still in the null space. Yeah, that works. Oh wait, then how many? I believe so. Yeah, I am. Oh, okay. Okay. Yeah, it's the same problem, except uh for the special solution we're given 1, 1, 1, right? Which is a little harder to work with because we don't have a 0 in there. But I'm not sure if that makes a difference. No, it does not. It does not. Okay, I'm trying to see what I did for problem 3B on the homework. Okay. Um, yeah, it's fairly straightforward. I can share my solution to 3B. Yeah, it's pretty easy actually. So with the particular solution, you know the last column, the variable corresponding to the last column has a 0, right? Which means which usually indicates, not usually, In this case, it indicates that the last column is free because we know it's a 3 by 2. If it's a 3 by 2 and the last column has 0, that means the last column is probably free. Uh, I think so. I think so. Yeah, the third column is free. And so then we know that the third column is free, so we set the third column equal to A and B. We set the everything else equal to 1. We set the pivots equal to 1, 0, and 0, 1. Then we multiply it by the special solution, and we set that equal to the 0 vector, because we know that the matrix times the special solution equals the 0 vector, because that's the definition of a special solution. And then we solve. So we say 3 plus A equals 0. So A equals -3. Then we say 3 times, then we say 1 times B equals 0. So B equals 0. So then this is our matrix. Yeah. So this is our matrix. And then we find, okay. Is this here? Like here? Oh, yeah, yeah. I have no idea what's going on. For my answer? Well, I found B. But that's just multiplying. Let me make sure I got this right. Nah. No, I don't. FERPA. Oh yeah, I got it right. Yeah. So the way I did it is it worked for this problem at least. I guess so. For problem 10 on the textbook, what you would do is set, well, we'd say A times 1, 1, 1 equals the 0 vector. Since the last entry of the particular solution is 0, we recognize that the last column is free. So we have a 1, or no, yeah, a 1, 0, A, 0, 1, B, times the special solution, which is 1, 1, 1, equals 0. So 1, 0A times 1, 1, 1 equals 0, which means 1 plus A equals 0, so A equals -1. 1, 1, 1 times this row equals 0. So 1 plus B equals 0, so B equals -1. So you substitute A and B equal -1 to this matrix. So you get 0, 1, 0, -1, 0, 1, -1 times your particular solution equals B, and you solve for B. Which will give you 1, 0, -1 times 2, 4, 0, 2. Yeah, and 1 and 0, 1, -1 times 2, 4, 0 will be 4. So you'll get 0, 1, 0, -1, 0, 1, -1 times x equals 2, 4. And I believe that's the answer that they got in the solutions. Yeah, but it's the one they got. So we know for a fact it works. Yeah, I need to study this a lot more. Just this. Yep. I think I'm done. Yeah, I mean the rest of the recommended problems, yeah, they're repeats, and some of them I don't feel are relevant. Yeah. Anyone have any questions?
I'm good. Thank you.
Okay. Yeah. Let's meet tomorrow. Oh, I want to do 10 p.m. tomorrow. I'll be a little busy.
That works.
Okay.
All right, y'all.
Yeah. See you guys later.
Thanks, guys.
Are you recording? Has it stopped?